you go. Sorry, this always takes a while. Can't get it right away. Okay. Book ready here. Okay, so let's see, that's done. We're sort of here. I'm going to aim for 11.4 and maybe 5 today. Okay. 11.4 is a little bit longer section, but 11.5 is shorter. So I may be able to do both of them. We'll see how it goes. Okay. So time-wise, I'm ahead of schedule still. So I'm aiming now for 11.4, maybe 11.5. Let's see how it goes. Okay, I was done with 11.3. I'm finished with the integral test. So 11.4 is on the comparison tests, plural. 11.5 is something called alternating series test. Don't worry if you don't write that down. I'm going to show it to you shortly. Okay. Okay, so the quiz. This is a typical theme for getting a sequence or series alternating. -1 to the n, or n plus 1 or n minus 1. N plus 1 and n minus 1 is to force the first term to be positive, because if I plug in 1, right, then 1 plus 1 is 2. -1 squared is 1, so that would make the first term positive. You could also do n minus 1, but if you left it as -1 to the n, then that makes the first term going to be negative, right? So it starts off with a positive. So 1, -1, 1, -1, 1, right? Just alternates. So for just the numerator would go +1, -1, +1, -1, +1. Okay, you plug in 1, you get 1. Plug in 2, you get 3, 5, 7, 9. Okay. This one, you basically double and add 1. So you keep doubling and add 1. Double, add 1, double, add 1, double, add 1, double, add 1. That's pretty much about it. Okay, this one converges to 1. It's pretty easy to see that that's the case, but the limit as n approaches infinity of n over n plus 2. It's sort of obvious, or you could do L'Hopital's rule, right? So 1 over 1 or 1. Even if you just take it literally, plug in a big number, 1,000,000 divided by 1,000,002, 1. Okay, and number 4 diverges. You'd have sine of 1, sine of 2, sine of 3, and so on. Well, we know the way the sine function works from trig, it just goes up and down, up and down. It just bounces back and forth between -1 and +1, never approaching any one number. Okay, so this one diverges. You can just put D for diverges. Okay, so that's that. All right, so we're going to get started now on section 4, which is on the comparison tests. Okay, I just alluded to it last time. Oops. Lost my page there. So 11.4, the comparison tests. Page 727. So one test is called the comparison test. Okay, so it's on the bottom of 727. I'll give you my variation of it. It's similar. Okay, first thing you'll notice is that, yes, if we don't really care whether we're indexing from n equals 1 to infinity or 2 to infinity, we know it's going to be infinity. Then we just don't even put the index. Just put the summation symbol. Summation a sub n, summation b sub n. That's okay if we don't really care. Okay, we're going from 1 to infinity or 2 to infinity, whatnot. Okay, now what they have is correct, but I'll show you my version, which I think might be easier to remember if you had to. Okay, so 11.4, the topic is the comparison tests. One is called the comparison test, CT. The other is the limit comparison test, LCT. Okay. The comparison test is easier to understand, I think, but the limit comparison test is actually more useful. Okay. It's useful in more problems. Okay, let me start with the comparison test. And I'll start off with this picture. Okay, now we know that for series, there are finite terms. You can only plug in 1, 2, 3, 4. But if we believe the integral test is true, then we can just convert to the corresponding integral, right? If the integral converges, the series converges. If the integral diverges, the series diverges. So let me think in terms of an integral. Okay, so a sub n is above b sub n. Okay, so what I have here is correct, but pretend you don't see it. It's too late now. But so a sub n is greater than or equal to b sub n for all n. Okay, so here are the two scenarios I want you to consider. Suppose b sub n diverges, blows up, goes to infinity. You look at the picture. B sub n goes to infinity. What does that tell me about a sub n? It also diverges, right? How can a sub n converge to a real number if something smaller than it already diverges, right? So if b sub n diverges, a sub n also diverges. Other situation, let's take the bigger one, a sub n. Suppose the a sub n converges. What do we know about b sub n? Also converges, okay? If a sub n converges to a real number, how can b sub n blow up, right? It stays below something which converges, right? That's basically the comparison test. Okay. So here's my version. As you can see, it's a lot less writing than what the book has, right? So I use C instead of convergent. I use D instead of divergent. Otherwise, they're equivalent. So if you like to use the book's wording on page 727, you may. But if you want to save space, I compacted into this. So here's the picture. A sub n is greater than or equal to b sub n. If summation of a sub n converges, summation of b sub n also converges. If summation of b sub n diverges, summation of a sub n also diverges. Okay, just look at the picture. Right, so these are the comparison tests. Now, I'll quickly mention the two other situations where you can draw no conclusion. And I think you can tell by the picture. Okay, so you can draw no conclusion if, okay, suppose you know that summation of a sub n diverges. The bigger series diverges. So what does that tell me about b sub n? I can't tell, right? It's smaller, so it might converge, it might diverge, right? You can't tell by the comparison test. Okay. And similarly, what's the other situation where you can't tell anything? Suppose summation of b sub n converges, right? The smaller one converges. What about the bigger one? Can't say. It might converge, it might diverge, right? So you have to be careful when you're doing the comparison test that you don't make the incorrect comparison, right? And I think this picture does it for you. So again, I won't show you the text because it's the same, but the book's heavy. I don't want to keep showing it to you. Okay, so again, just think of this picture. You have a comparison between two series. I know I drew it as integrals, but we'll take them as series. Okay, the smaller one diverges, blows up. The bigger one has to diverge. Okay, and the other way you can use comparison test is if the bigger series converges, that means the smaller one converges. Okay. All right, so before I do any of the homework problems, I'll start off with some examples and some rules to follow. Okay, so first I want to talk about something called the reciprocal rule. You sort of already know it. Okay, if A and B are both positive, if A is bigger than B, then 1 over A is less than 1 over B, right? The reciprocal is reversed. So here's a simple example. 3 is greater than 2, right? If I take the reciprocals, then the inequality goes the other way. 1/3 is less than 1/2. Is that right? Okay, so that's the way that works. All right. So let me show you some of this. Do you agree with this statement? N minus 1 is less than n, which is less than n plus 1. That's true for all n. Okay? Specifically, we're doing in positive integers now, but we know that's true. Right? I mean, just say n is 7. 7 minus 1 is 6, less than. 7 plus 1 is 8, bigger than. Okay, so therefore, by the reciprocal rule, when I take the reciprocals, it goes the other way. 1 over n minus 1 is greater than 1 over n, which is greater than 1 over n plus 1. Is that right? Okay, and let me get the right page in the book here for a moment. All right, now, what do I know about summation of 1 over n? That diverges because it's a harmonic series. Okay, so when you have to list a reason for summation 1 over n diverging, just say it's the harmonic series. Now, what about summation of 1 over n minus 1? 1 over n minus 1 is greater than 1 over n. So summation 1 over n is bigger than a series which diverges, and specifically diverges to infinity. Therefore, by the comparison test, summation 1 over n minus 1 also diverges by the comparison test. However, summation of 1 over n plus 1, I can make no conclusion by the comparison test, CT, right? This one blows up. This is a smaller series. It's smaller, so I can make no conclusion. Okay, by the same token, let me show you this. Okay, do you agree with this? N squared minus 1 is less than n squared plus 1. Pretty much the same reason as before, right? Take n squared, if you subtract 1, it's smaller. If you add 1, it's bigger. Therefore, by the reciprocal rule, it goes like this. Same logic, right? Greater than, greater than. 1 over n squared minus 1 is greater than 1 over n squared, which is greater than 1 over n squared plus 1. Now, what do I know about summation of 1 over n squared? Converges. Reason, it's a p series with p equal to 2, which is greater than 1. Okay, so remember, we have a shortcut now for the p series. You can put that in your next formula sheet. Okay, so the p series was from the integral test. Right? It's a variation of the integral test. Let's see if I can find that for you again. Formula for p series. Page 722. The p series summation of 1 over n to the p. It's convergent if p is greater than 1, divergent if p is less than or equal to 1. So the comparison number is 1. This is n squared, so it's a convergent p series. Therefore, anything smaller than that, let's see, this one is smaller. So summation of 1 over n squared plus 1 also converges by the comparison test. But the bigger series, this is bigger than something which converges. Okay, so that's this picture. The smaller one converges. What does that mean about the bigger one? Don't know. It might converge, it might diverge. Right? So summation of 1 over n squared minus 1, no conclusion by the comparison test. Okay? So that's what we have so far. All right, now, still, something about these, I hope you would see, you would think these all should behave kind of the same. I mean, minus 1, plus 1. Remember, n is going to become super big. A million, a billion, a trillion. If I get that big, if I take away 1 or if I add 1, it's really not much difference. You would suspect the same thing's going to happen to all of these just because they're quote unquote sort of alike. They're very similar to the harmonic series. Okay? I cannot make any conclusion from the comparison test. Still, I'm going to say this one should diverge because it's kind of like a harmonic series. Likewise, for this series, I cannot make any conclusion with the comparison test because summation 1 over n squared minus 1, I can't make any comparison from the comparison test. Still, we should be able to say, you know, when n is super big, plug in a million, you're talking about 1 over a million squared. It should not make much of a difference if I add 1 or if I subtract 1. I still think this should converge, right? That's what we want to do. Limit comparison test, LCT. So I'll show you the limit comparison test now in the text. Whoops. Okay, page 729. Suppose summation of A sub n and summation B sub n are series with positive terms. Okay, so the key thing here is we have to have positive terms. The idea is that, can I compare the given series to another easier series, quote unquote, an easier series, and I know how to analyze the other series. Okay, if the limit as n approaches infinity of A sub n over B sub n is equal to C, where C is a finite number and bigger than 0, then either both series converge or both diverge. It's kind of like the integral test. Okay, if one converges, the other converges. If one diverges, the other one diverges. Okay, and to be honest with you, a lot of the times this C is going to be 1. Okay, but technically it could be any finite number, not 0. That's a lot of numbers. It's really any positive number. Okay, well, we're only doing positive quantities anyway. We're really just saying if you get a limit that's not 0 and it's not infinity, that's a lot of numbers. Not 0 and not infinity, then both converge or both diverge. Okay. What you're doing is comparing it to a series which is more comfortable, quote unquote. Okay. And yes, in practical terms, a lot of times this will turn out to be 1. Okay, so how do I do that now? Okay, so let me show you how that works. Let's see. So let's take a look at this one. Summation 1 over n squared minus 1. By the comparison test, I could make no conclusion. Still, I kind of feel like saying, you know, this should behave like summation 1 over n squared. I think it still converges, right? If I plug in, remember n is approaching infinity, so I plug in 1,000,000. There's not much difference between 1 over 1,000,000 squared and 1 over 1,000,000 squared minus 1. Okay? So then I would use the limit comparison test. So here's the way limit comparison test works. Okay, you're given a summation of 1 over n squared minus 1. I will compare it to summation of 1 over n squared because I know what happens to summation 1 over n squared. Okay, now, according to the theorem for limit comparison test, you take the ratio of one to the other. Which goes on top, which goes on the bottom, it doesn't matter. Okay, so I'm going to put 1 over n squared minus 1 divided by 1 over n squared. Take the limit as n approaches infinity. Okay, multiply top and bottom by n squared. I have limit as n approaches infinity of n squared over n squared minus 1. Okay, you can tell by inspection that's going to be 1. But if you want to do it formally, like the method of Calc 1, divide top and bottom by n squared, or you can do L'Hopital's rule. But I want to remind you of this technique because you still want to know this technique. Divide top and bottom by n squared. Limit n approaches infinity of 1 over 1 minus 1 over n squared, and that comes out to be 1. Okay, that's perfect. Okay. In fact, this is the ultimate that one series behaves like the other. Okay. One series behaves like the other if in the limit as n approaches infinity, the ratio is 1. Okay. In other words, as n gets bigger and bigger and bigger, these two series are more alike. Okay. Remember, you're taking a fraction. When is a fraction equal to 1? A fraction is equal to 1 when the top and bottom are the same. Okay. Here they're not the same, but they're quote unquote almost the same. In the limit, the ratio is 1. Right? Because you have 1 over 1,000,000 squared minus 1. This is 1 over 1,000,000 squared. They're practically the same. The ratio is 1. So by the limit comparison test, okay, this could actually be any positive number, just not 0, not infinity. So whatever happens to one happens to the other. So what do I know about summation of 1 over n squared? It converges. Reason P series, P equals to 2 greater than 1. Therefore, the original series, so S will mean the original series, also converges by the limit comparison test. So whatever happens to this one happens to the other one. Okay, so that's how limit comparison test works. You find a companion series which is easier, quote unquote, easier to work with. Okay. Establish this limit. C can be any positive quantity, just not 0 and not infinity. Then both series converge or both diverge, means whatever happens to one happens to the other. Okay. Oh, yeah. Sorry. You say which one should go on top, which one should be in the bottom. It doesn't matter. Okay, because let's suppose I do it this way and the limit comes out to be 7. It's not 0, it's not infinity. If I flip it, the ratio would be 1 over 7, which is still not 0 and still not infinity. So you're good either way. Okay, so you can pick either one to be on top, either one on the bottom, which means you can pick whichever you want. Okay. All right, so I'm going to start showing you some problems, and I'm noticing that my problems don't match yours for the most part. So if it does, great. If it doesn't, you're still learning the material anyway, because they changed up the problems on me. But we'll go with it. All right, so 11.4, summation n over 2n cubed plus 1. Okay, now, limit comparison test is usually the easier way to go. That way you don't have to be as careful as to say, okay, this one's bigger, this one's smaller, right? Because for strict comparison tests, you have to make sure, right, which one is bigger and which one's smaller. So if A sub n converges, B sub n converges, but you have to make sure this is bigger than that, right? And if B sub n diverges, A sub n diverges, you have to be careful. Limit comparison test, you don't care which one's bigger, which one's smaller, okay? You just do the ratio. All right, so for this one, summation n over 2n cubed plus 1. Say, how do I know what to do? Okay, so for super big n, I would ignore the plus 1, right? So that's the idea. Look at this. What does that look like? 1 over 2n squared. So that's my comparison series. Summation of 1 over 2n squared, right? Get rid of things that quote unquote don't matter in the long run. Okay. And notice, yeah, I'm starting to leave this off. It's not just being sloppy, but it's just you don't want to keep writing it. N equals 1 to infinity, n equals 2 to infinity. Quite often we just leave it off. It's not that important. Okay. I mean, it's almost always going to be infinity up here. The bottom's going to be 1 a lot, but it might be 0, it might be 2, whatever. Okay, now I established the ratio. So what is the ratio of this to this? So I did limit n approaches infinity, n over 2n cubed plus 1 divided by 1 over 2n squared. Okay, clean it up, multiply top and bottom by 2n squared, so that's gone. 2n cubed divided by 2n cubed plus 1. This time I decided to go for L'Hopital's rule. Remember L'Hopital's rule, this is infinity over infinity. So I can get the derivative of the top and the derivative of the bottom, 6n squared divided by 6n squared. The limit is 1. Okay, and what do I know about summation of 1 over 2n squared? Factor out the half. Remember, if you multiply by a non-zero constant, okay, that will not affect convergence or divergence. Okay. Now, for the convergent case, it won't converge to the same number, but it'll still converge, period. So we're doing a lot of problems now. You might be kind of dissatisfied with that, but all we're going to be able to say sometimes is that the series converges, period. What number does it converge to? Don't know. Maybe we can't tell. Maybe we don't care, but it just converges to some number. Okay, so 1/2 summation 1 over n squared. That converges because this is a p series. P equals 2 greater than 1. Okay, so this new series that I invented, this series converges. Therefore, whatever happens here, happens here. So the original series, so S is the original series, just like when I was doing the integration, capital I was the original integral. So capital S is the original series. It also converges, not by CT, not by the comparison test, but limit comparison test. Okay, so we're doing the limit comparison test now. Okay. All right. And let me show you number 5. And I'm noticing this does match your number 5, I think. Yeah, maybe it does. Okay. Summation n plus 1 over n radical n. Okay, so again, my advice is anything that is insignificant in the long run, forget. Remember, we're talking about n approaching infinity. When n gets super big, what gets lost, quote unquote? The 1. So forget about the 1. If I forget about the 1, it'll be n over n radical n. N's cancel out, 1 over radical n. So I would compare to summation of 1 over radical n. Notice we're not that careful as to which is bigger and which is smaller. It doesn't matter. Just do this. Now I established a ratio. For almost all of these, the ratio will be 1. Okay, n plus 1 over n radical n divided by 1 over radical n. Multiply top and bottom by radical n. That drops out, that drops out. N plus 1 over n. You can do L'Hopital's rule, or another trick is to actually divide it. N divided by n is 1 plus 1 over n. And now when n gets super big, that's 0. 1 plus 0 is 1. Okay. So I took the ratio of the original series to my made-up series. How do you know what to make up? Usually you can tell by saying, okay, ignore constants, right? It's not significant in the long run. And as long as this comparison limit is any positive number, but quite often it's 1, then whatever happens to this also happens to this. Okay, notice I'm not really caring about which is greater and which is smaller. The limit comparison test, you don't have to worry about it. Now, what do I know about summation 1 over radical n? That's 1 over n to the half. That diverges. That's a divergent p series because p is 1/2, which is less than 1. Right, so this made-up series diverges. Therefore, the original series, which I'll abbreviate SD by limit comparison test. Okay. Notice a nice thing about these abbreviations. Series diverges by limit comparison test. It's a lot shorter than writing series SERIES DIVERGES by, and then spell out limit, spell out comparison, spell out test. That's why we have these abbreviations. You just want to get it down quickly. We know what we're talking about in this particular case. All right. Okay, I haven't done a whole lot of comparison tests yet. So is there a comparison test? So number 9, yeah, it matches this one. Summation ln k over k. All right. Oh, by the way, you could do this by the integral test. That's integrable, right? If I had ln x divided by x, I could do a u substitution. Okay, but we probably don't want to do the integral test. Is there something better? Okay. A hint is, and yeah, it doesn't matter if you have k. Index can be k or I or n. You know, same thing. All right. Now we don't know too much about ln k, but we know 1 over k. Right. 1 over k is our harmonic series, and we know that diverges. All right. So ln k is greater than 1 for k greater than or equal to 3, it turns out. Okay. The natural log of e is 1. E is like 2.7. So for k greater than or equal to 3, ln k is bigger than 1. So this is the time where I'm going to use CT, comparison test. Okay. For k greater than or equal to 3, okay, so it's not true for 1, ln 1 is 0, it's false. It's not true for 2, ln 2 is like 0.693, that's not true. But starting with 3, ln 3 is, I forgot, something like 1.09 or whatever. It starts to become bigger than 1. Okay, so for k greater than or equal to 3, which is still okay, ln k is greater than 1. Divide both sides by k. K is positive, so that's fine. So I'm going to do comparison test. What do I know about summation 1 over k? Diverges. That's a harmonic series. And this is a series which is bigger than one which diverges. So that is this picture. The smaller series diverges, blows up. This one has to blow up. It cannot converge to a number. How can this approach a number when something smaller than it blows up? All right. So what do you say as a proof, so to speak? And this is the kind of thing you have to do in this entire chapter. This converges or diverges because. So you write stuff like I've been doing. You can't just say converges or diverges. I mean, you can flip a coin and get it right 50% of the time, but you have to tell me this is the reason why this series converges, or this is the reason why it diverges. Okay, summation 1 over k diverges. The reason is because it's the harmonic series. Okay, therefore, any series bigger than it term by term, well, for k greater than or equal to 3, would also diverge. Okay, so summation k equals 3 to infinity of ln k over k also diverges by the comparison test. So now I can go back and say summation k equals 1 to infinity of ln k over k also diverges because I put in a finite number of terms. Okay, so last time I said if you put in or take out a finite number of terms, that will not affect convergence or divergence. Okay, I mean, this thing already blows up, right? So if this thing already blows up, I go back and put in the first two terms, it would still blow up, so to speak. Okay. All right, and then let's see. My 13 looks like it's different, but be that as it may. Summation arctan n over n to the 1.2. Okay, we have to know what happens to arctan. Okay, so it's worth knowing the arctan, so a little timeout. Arctan looks like this. Y equals arctan x, which can also be written as inverse tangent of x. Okay, this is y equals pi over 2. This is y equals negative pi over 2. Y equals pi over 2. Y equals negative pi over 2. Okay, in other words, the limit as x approaches infinity of inverse tangent of x is pi over 2. Okay, you can put that on your cheat sheet if you wish, even the graph of arctan. Okay, and I'm not sure if I showed you this before or another class. Okay, so I'm going to make this disappear, but if I'm going too fast, you can check the recording later. But this is what arctan looks like. So when x approaches infinity, or n approaches infinity for series, then the values approach pi over 2. You can check it out on a calculator, and I have to make sure that I'm in radian mode. Okay, so I'm in radian mode. So, sorry, if you just do arctan of a super big number, okay, inverse tangent of, I just typed 1 and a whole bunch of zeros, 1.5707, okay, and punch in pi over 2. Every digit's the same, okay, which it actually isn't, but it's very close. It's correct to what, 10 digits or something like that. So if you ever forget the limit, you can just punch in a super big number and you see it's about pi over 2, 1.57, blah, 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 blah. Okay. But it stays below pi over 2. Okay, that's the key thing. So what I'm trying to share with you here is that I'm going to compare it to summation of pi over 2 over n to the 1.2, which I can factor out to pi over 2. Pi over 2 times the summation of 1 over n to the 1.2. All right, so I take out the constant. Pi over 2 is 1.57. Again, if I multiply any series by a non-zero constant, that would not affect convergence or divergence. So if this thing converges, or sorry, if this thing converges, then this thing converges. If this thing diverges, then this thing diverges. Okay. So what I'm trying to say is this: arctan n over n to the 1.2 less than or equal to pi over 2 over n to the 1.2. Okay. Start off with this. Arctan n is always less than or equal to pi over 2 in the picture. And then divide both sides by n to the 1.2, which is a positive quantity. Right, we're only plugging in positive ends. Okay, and then the new series, summation pi over 2 over n to the 1.2, take out the pi over 2. That's a convergent p series. It converges because it's a p series. P is 1.2, which is greater than 1. Okay, so the bigger series converges. Smaller series converges by the comparison test. Okay, so therefore, this dot, 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 by the way, means therefore. Therefore. So if you see me or anybody else do a dot, 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 like that, it means therefore. So therefore, the series also converges by the comparison test. This was the comparison test, CT. Okay. Okay, then I was going to do my 15, and it looks like it matches this time. Okay, 4 to the n plus 1 over 3 to the n minus 2. Okay. Can you guess what I'm going to throw out in the long run? Minus 2. So forget that. Now, I want these to be the same. This is n plus 1 and this is n. The way you can get around that is to write 4 to the n plus 1 as 4 times 4 to the n, right? So do you agree this is 4 to the n plus 1? Right, so if I never mind about the -2, forget the -2, I'm trying to claim that this is the same as this. This is 4 times 4 to the n, 4 to the n plus 1, and that's 3 to the n. Because again, I'm multiplying by a non-zero constant, 4. All right, so that's my comparison series, compared to summation of 4 times 4/3 to the n. Which I can write as 4 to the n plus 1. All right, so take the ratio. This is the original a sub n, 4 to the n plus 1 over 3 to the n minus 2. This is the same thing, except forget the minus 2. 4 to the n plus 1 over 3 to the n. Limit n approaches infinity. Okay, so if you divide by a fraction, you multiply by the reciprocal. So leave that alone, times the flip, right? These cancel out. 3 to the n over 3 to the n minus 2. And again, you can do L'Hopital's rule, or this time I divide top and bottom by 3 to the n. Okay, so 3 to the n over 3 to the n is 1. This 3 to the n over 3 to the n is also 1. Minus 2 over 3 to the n. If you can't read that, that's 2 over 3 to the n. But I'm saying that approaches 0. 2 over 3 to the n approaches 0 when n gets big. So the ratio is 1. Okay. Which means whatever happens to this series happens to this series. Okay, so what do I know about this series? 4 times 4/3 to the n. It's a geometric series, right? See, how can you tell? Well, stop and think about it. Normally, when you see something that looks like that, okay, something to the n, the common ratio is 4/3, right? I mean, you plug in 1, you have 4/3 to the 1. Plug in 2, 4/3 squared. So what did you do? You multiply by 4/3. Then 4/3 cubed, you multiply the previous one by 4/3. So it's a divergent geometric series. So, and you should tell me stuff like this too. So it diverges because of the geometric series, okay, because R is 4/3, 4/3 is bigger than 1. Okay. Therefore, the original series also diverges by the limit comparison test. So I did the limit comparison test this time for problem 15. Okay. All right, so you see sometimes we have comparison tests, sometimes limit comparison tests. You say, how do you know which one to pick? Okay, so if I see a series behaves almost like some other, like this one, right? To me, the dead giveaway is, okay, when n is real big, forget about the plus 1. Then you say, oh yeah, that's like 1 over 2n squared. So I should do LCT, limit comparison test. This one, say, oh yeah, forget about the plus 1. Then it's like 1 over radical n. Okay, and the one we just did, let's see. Yeah, this one, right? You would say for super big n, forget about the minus 2. So that told me what to do. Now, for this one, I couldn't use limit comparison test. There wasn't anything nice that I could use. But I do know 1 over k, summation 1 over k, that's a divergent harmonic series. So that led me to believe I should do comparison tests in that instance. Okay. Similarly, for something like 13, arctan over n to the 1.2, that's so weird, right? You can't get anything that's kind of like that. So I just said, okay, well, don't worry about it. But I do know arctan is less than pi over 2. So I said, okay, let me compare it to pi over 2 over n to the 1.2. And then I say, oh yeah, I can figure out what happens here because it's a p series. Okay, yeah, this chapter has a lot of different rules for convergence and divergence, right? So start getting comfortable with all those different things. Okay, so next one I'm going to show you was my 21. Let me see if it matches. I don't think it matches. Nope, too bad. Oh well. Here's what to do. Okay, summation radical n plus 2 over 2n squared plus n plus 1. Okay, so here's the game you want to play, sort of. For real big N, it's essentially that. Square root of n over 2n squared. Right? For super big N, the 2 gets lost. 2n squared, you can just forget about the n and the 1. So my comparison series would be, and you can even forget about the 2, it's n to the 1/2 divided by n squared. N to the 1/2 n squared. That's like 1 over n to the 3/2. Okay? Because then I know what to do with this. It's a comparison series to the p series. All right, so my comparison series is 1 over n to the 3/2. So I'm doing limit comparison test. All right, so take the ratio of the original. Don't write the summation, of course. Write that thing divided by 1 over n to the 3/2. And because of the way I set this up, I'm going to rewrite 1 over n to the 3/2 as this. Radical n over n squared. That's probably better anyway, because that's what I have. This is still 1 over n to the 3/2. I mean, that's how I got it in the first place. Okay, so are you okay? This is still 1 over n to the 3/2. This is n to the 1/2 n squared. Okay, and of course, when you divide by a fraction, you multiply by the reciprocal. So write it like that. Okay, the limit of a product is a product of limits. I will put these two together, radical n plus 2 over n, and put these two together, limit n approaches infinity of n squared over 2n squared plus n plus 1. Okay, so this one's going to be 1. You can write it as 1 plus 2 over n. This one, I'll play the trick of dividing top and bottom by n squared, but you could also do L'Hopital's rule. I'm trying to remind you of all the different techniques that we had. Okay, so this is clearly 1. Okay, when n gets big, square root of 1 is 1. This is 1 over 2 plus 1 over n plus 1 over n squared. Now when n gets super big, that goes to 0, that goes to 0. So I have 1 times a half, which is a half. Okay, so the ratio of the two in the long run is a half. That's okay. That's allowed. That's okay. So that does mean whatever happens to one happens to the other. Okay, so I just have to figure out now what happens to my easier series, summation 1 over n to the 3/2. So summation 1 over n to the 3/2 converges. Why? It's a p series. P is 3/2, which is greater than 1. Therefore, the original series also converges by LCT, limit comparison test. Okay, so whatever happened to the one happens to the other. All right, so we have comparison test and we have limit comparison test. Okay. Yeah, looks like a lot of the ones here aren't going to match, but be that as it may. So my 25 doesn't look like it matches, but that's okay. By the way, you can see I'm even starting to get lazy. Well, it's not really just lazy. It's after a while, you're writing so much stuff, you don't feel like keep writing n equals 1 to infinity or 2 to infinity or whatever, right? Okay, n to the 4th plus 1, n cubed plus n squared. Okay, so in the long run, for super big n, what I'm going to think about the top? I'm going to forget about the 1. So it's square root of n to the 4th, which is n squared. So I think of the top as almost n squared. How about the bottom? For super big n, drop that, n cubed. Right? Essentially, it's n squared over n cubed. Right? When n is real big, the 1 is insignificant. This is like n squared. The bottom, n cubed plus n squared falls behind. It's basically n squared divided by n cubed. So what's my comparison series? 1 over n. N squared divided by n cubed, the harmonic series. Okay, now prove the limit. Okay, the limit's going to be 1. Again, you're allowed to have any real number by LCT, limit comparison test. Any real positive quantity, not 0, not infinity, and it has to exist. Okay, so limit n approaches infinity of the original divided by 1 over n. Okay, multiply top and bottom by n, so that's gone. So I now have this. Okay, you have to temporarily ignore the red, if you can even do that. Okay, so I have n times radical n to the 4th plus 1 over n cubed plus n squared. Okay, now what did I do here? I divided top and bottom by n cubed. Divide this by n. Divide this by n squared by putting n to the 4th inside. So the stuff I haven't read is n cubed. There's n. Here's n squared outside, n to the fourth inside, and divided this by n cubed. The reason why I do that is because I know I want that to be 1, I want that to be 1, and I want that to be 1 over n. So this drops out completely. Limit n approaches infinity of 1. So that becomes square root of 1 plus 1 over n to the fourth. This is 1 plus 1 over n. And there it is. When n gets super big, 1 over n to the fourth, that approaches 0, that approaches 0. So I have square root of 1 over 1, which is 1. So whatever happens to this series happens to this series. They are quote unquote alike. So what happens to summation 1 over n? Diverges because it's a harmonic series. Therefore, the original series also diverges. Reason, limit comparison test. Okay. All right, what time is it? 8 o'clock. I only have 3 more for this entire section, and I think I'll be done. So yeah, let me go ahead and finish it. In fact, I'll be done with the entire section, and then after the break, I can do 11.5. Okay, so just bear with me. Let me finish these last ones up. 27, 29, and 31, they do match. Okay, so these do. Okay, 1 plus 1 over n squared e to the negative n. Okay, now this is so weird, it doesn't look like I can compare it to anything. Right? But let me go ahead and write some of the terms out. See, sometimes if you're not sure what happens, just write some terms out. Okay, that's like e to the n on the bottom, right? So e to the first, e squared, e cubed, e to the fourth. Okay, plug in 1. 1 plus 1 is 2. 2 squared is 4. Plug in 2. 1 plus a half is 3 halves. 3 halves squared is 9 fourths. Plug in 3. 1 plus a third, 4 thirds. 4 thirds squared, 16 over 9. Plug in 4. 1 plus 1 fourth, 5 fourths. 5 fourths squared, 25 over 16. Okay. All right, so what's happening to the terms? The numerators are getting smaller, right? Now, pretend I didn't have the numerators. Pretend all the numerators are 1. Suppose it's at 1, 1, 1, and so on. 1 over e squared, 1 over e cubed, 1 over e to the fourth. That's a geometric series. What do I keep multiplying by? 1 over e. In other words, if I only had that, e to the negative n or 1 over e to the n. The common ratio is 1 over e, 1 over 2.7. That's between negative 1 and 1. That would converge. Right? That tells me, that gives me a guide as to what I should do with this one. We think this thing will converge. Okay, it behaves kind of like 1 over e to the n. Okay, so what should I do? I think this thing converges, so I need to make the numerator something more easy to deal with. 4, 9 fourths, 16 ninths, 25 sixteenths. So I have to use the principle of the comparison test, CT. Okay, so in other words, I think it's going to be this situation. The smaller one converges, therefore the bigger one converges. I take it back, the other way around. The bigger one converges. Bigger one converges, therefore the smaller one converges. So I want to change this mess in the numerator to a series which is bigger, but I know it converges. So 4, 9 fourths, 16 ninths, 25 sixteenths, they're getting smaller, right? So my comparison series is 4 over e to the n. Summation n equals 1 to infinity of 4 over e to the n. In other words, this new series, I'll call it S1, is 4 over e to the 1 plus 4 over e squared plus 4 over e cubed. Okay, so you can tell that 4 over e to the n is greater than or equal to this 1 plus 1 over n weird stuff, e to the n for all n, right? Here it's 4, 9 fourths, 16 ninths, 25 sixteenths, and so on. That's definitely going to be smaller than if they were all 4s, and the denominators are the same. So this is the bigger series. Okay. So I have a nicer series, 4 over e to the n. And what do I know about summation of 4 over e to the n? That's a convergent geometric series, right? Because it's 4 over e squared, 4 over e cubed. The common ratio is 1 over e. Okay, that's between -1 and 1, or you can say absolute value of r is less than 1. Okay. So this series converges. Therefore, any series, as long as we're only talking about positive terms, okay, I haven't mentioned it much, but these are only with positive terms. These are all positive. Then the smaller series, which this one is, will also converge. This is by the comparison test, not limit comparison test, comparison test. So the series converges by the comparison test. Okay, yeah, I know it's getting late. Maybe I won't finish. That's okay. 29, yeah, we'll do 29, then we'll break. So summation 1 over n factorial. 1 over 1 factorial, 1 over 2 factorial, and so on. Write some of the terms out. 1 plus a half plus 1/6 plus 1/24 plus 1 over 120. Right? Remember about the 4 factorials? 4 factorial means 1 times 2 times 3 times 4. 5 factorial is 1 times 2 times 3 times 4 times 5, which is 120. Okay. This looks like it should converge. Right? The numbers are dropping. So let me compare it to hopefully a bigger series, summation of 1 over n squared. Okay, so I write some of the terms out as summation of 1 over n squared. 1 plus a fourth plus a ninth plus 1/16 plus 1 over 25. Okay, if I ignore the first 3 terms, don't look at the first 3 terms. Okay, look at the 4th term and on. Which is bigger, 1 over 24 or 1 over 16 by the reciprocal rule? This one's larger, right? Which is bigger, 1 over 25 or 1 over 120? 1 over 25. Okay, so for n greater than 3, for n bigger than 3, not true here, not true here, not true here, but starting with the 4th term and on. I mean, 6 factorial is 720. This would be 1 over 720. That's, 720 is way bigger than the next one here, which would be, what, 36? Okay, so for n greater than 3, 1 over n factorial is less than 1 over n squared. Okay, that's the way I want it. The bigger series converges. Summation n equals 4 to infinity, because it's starting with the n greater than 3. 1 over n squared converges because it's a p series where p equals 2 greater than 1. Therefore, summation n equals 4 to infinity, that's a 4. 4. And that's also a 4. Summation 1 over n factorial also converges by the comparison test. And then I go back and put in the first 3 terms. So now put back in the first 3 terms. So summation n equals 1 infinity of 1 over n factorial also converges. So that's what we want to say there. Okay. All right, let's take a break. I have just 31 to go, and then I can start the next section. All right, so break time. Let me check what time is it. 8:07. Oh boy. Okay, how about let's start up again at 8:20? Okay, so 8:20 we'll start up again. All right, thank you. Okay, folks, it's 8:20, so we'll go ahead and pick up where we were. There's nothing in the chat, so I think we're good. All right, so let me go back and just do problem 31, and then I'll be finished with that section. Okay, so share the screen again. All right, so I'm almost done with 11.4, then I can start 11.5. 11.5, I think, is a much easier section. So let me just knock off this last one here. Okay, 31, and I think it's the same as the summation sine of 1 over n. Okay, well, see, sine of 1 over n. Well, I do know something about 1 over n, right? Our harmonic series. So let's see what happens in the ratio. So limit as n approaches infinity, sine of 1 over n divided by 1 over n. That's 0 over 0. When n gets big, this becomes 0. This becomes 0. Sine of 0 is 0. So I can do L'Hopital's rule. The derivative of the top is cosine 1 over n times the derivative of 1 over n. I'm just writing as 1 over n prime. Because at the bottom, I'm taking 1 over n prime. I can just cancel the 1 over n primes. That's fine. Yes, that's n to the minus 1, so the derivative is negative n to the negative 2. You don't have to do all that. This just cancels out. So when n gets big, I'm taking the cosine of 0, which is 1. So yes, whatever happens to one happens to the other. What happens to summation 1 over n? It diverges because it's a harmonic series. Therefore, the series also diverges by the limit comparison test. Okay. Okay, so that pretty much does it for 11.4. Okay, so that's done, and I'll start 11.5, okay, which is on alternating series. We've already seen alternating series. Okay, so let me make this disappear. 11.5, alternating series. All right, so we have a formal definition of an alternating series, page 732. Okay, so we know plus, minus, right? Or it might start with a negative. So the series could start either with a positive or negative, and then you just alternate. And we know how to make it too. We can either have a negative 1 to some power, like negative 1 to the n minus 1, or negative 1 to the n. Let's see, if I plug in 1, negative 1 to the 1 is negative 1. So that would make the first term negative in case you want the first term to be negative. But if you want the first term to be positive and you index beginning at 1, then you would go negative 1 to the n minus 1 or n plus 1. I like n plus 1 better, like positive. So, all right, so we want to have the alternating series test. As you might guess, you've got to have a series which is alternating. All right, so this is on page 732, 11.5. But again, I will give you my shortcut version of it. So you can put down what the text has, but I have the Melvin Home version, which of course I like mine better, but it's equivalent. So you have an alternating series, summation negative 1 to the n minus 1 or n or whatever. So it alternates, b1 minus b2, etc. b sub n plus 1 is less than or equal to b sub n. So the b sub n decrease in absolute value, and they approach 0. B sub n approaches 0. Then the series is convergent by the alternating series test. I don't feel like writing alternating series test. Can you guess what my abbreviation would be? AST, alternating series test. Okay, so I'll give you my version, which is hopefully a little bit more compact than what the author has. All right, alternating series test, AST. 3 things have to happen. Can you guess an obvious one for alternating series test? It has to alternate, right? And I'll abbreviate with alt. Got to be alternating. How can you tell it's alternating? Quite often with that -1 thing, right? Either -1 to the n or n plus 1 or n minus 1. The terms decrease in absolute value. That's equivalent to this. Okay. Now, if you go strictly by numerical value, it goes positive, negative, positive, negative. Well, a positive number is always bigger than a negative number, and a negative number is always bigger than a positive number, so you can't go, like that. But if you ignore the negatives, make them all positive, then the terms are decreasing. That's what we mean by the term decrease in absolute value, and they approach 0. Okay. Here's my abbreviation for the terms decrease in absolute value. Absolute value of a sub n is decreasing, arrow down. And a sub n approaches 0. Here's my abbreviation. A sub n approaches 0. Okay, so when you're trying to show something for alternating series test for me, you can either write out all these words, or here's my abbreviation for the whole works. You can put this on your cheat sheet. ALT, alternating. Absolute value of a sub n decreases. That means the terms decrease in absolute value, and a sub n approaches 0. Then, or therefore, the series converges by the alternating series test. Okay, so alternating series test, 3 things have to be true. Obvious one is alternating. Okay. What's a giveaway for the alternating? Quite often the -1 thing. Absolute value of a sub n is decreasing. That means the terms decrease in absolute value, and a sub n approaches 0. Then the series converges by the alternating series test. Okay, example. Summation -1 to n plus 1 over n. Okay, now by index beginning at 1, 1 plus 1 is 2. That makes the first thing positive. So 1 minus a half plus 1/3 minus 1/4. Okay, so if they were all pluses, that's our harmonic series. Can you guess a good name for this thing? Alternating harmonic series. Okay, so the alternating harmonic series is the same as the harmonic series, only it alternates, and starting with a positive. So it's +1 minus a half plus a third minus a fourth, and so on. Okay, this is just a side note. Okay, believe it or not, this thing converges to natural log of 2, which is about 0.693. And I will show you a proof of that later, believe it or not. So you will see where that comes from. But for now, just take it on face value. This approaches ln2, 0.693. Let's see some of the partial sums. Okay, 1 minus, okay, right here, this is 1/2, right? And 1/2 plus 1/3 is 5/6. That's like 0.833. Take away 1/4, that's 0.83 minus 0.25 is 0.583. So it does seem sort of reasonable. Okay, so look at this series. Is it alternating? Yep. Do the terms decrease in absolute value? That means if you look at the absolute value of the terms, 1, a half, a third, don't include the sign. If you include the signs, then it's obvious this decreases, increases, decreases, increases, right? Just because every positive is bigger than any negative, and any negative is smaller than any positive, it'll always go up, down, up, down. So decreases in absolute value. If you take the absolute value of all the terms, 1, 1/2, 1/3, 1/4, then it's decreasing. And the a sub n's approach 0. Yes, the terms approach 0. So the alternating harmonic series does converge, even though just the harmonic series itself diverges. So they were all pluses, right? 1 plus a half plus a third. We've shown that that diverges, but if you make it alternate, it converges. Okay, and I'll show you some examples of that now. Okay, this is not a proof, but a plausibility argument for the alternating series test on page 733. So they're going like this. Okay, so what are they trying to show? Okay, it's alternating. So they go to the right and then to the left and then to the right, to the left, right, alternating. Okay, but the terms decrease in absolute value. So when I switch back and forth, left, right, the amount that you're going back is less and less, right? So you go that way, then you go back, but not as far. Then you go this way, not as far, right? That's what it means to be decreasing in absolute value. And the terms approach 0. So after a while, it really, comes in. So it converges to a certain number that we call the limit S. Okay, so it does seem reasonable that that's the case. All right. Okay, so some examples now. Number 3. And a lot of these don't match, so I may just have to do them for you. Okay, negative 2/5 plus 4/6 minus 6/7, and so on. Okay. All right. Is it alternating? Yes, it's definitely alternating. But it looks like a sub n does not approach 0. In fact, look at how this thing is progressing. It alternates. The top goes 2, 4, 6, 8, 10. So the numerator, you just keep adding 2. The bottom goes 5, 6, 7, 8, 9. The numerators, you increase 2. The denominators, you increase by 1. So it looks like a sub n does not approach 0. Okay. So if a sub n does not approach 0, automatically the series diverges by the test for divergence, TFD, way back in section 2. Okay. If a sub n does not approach 0, the series diverges by the test for divergence. Okay. Let me see if I can show that to you quickly. Okay. 11.2, test for divergence, page 713. I call it TFD. Okay. If the limit as n approaches infinity of a sub n does not exist, or the limit as n approaching infinity is not 0, the series is divergent. Okay. Another way of saying that is that a sub n does not approach 0, which includes doesn't approach anything, limit doesn't exist, but also the limit might exist, it's just not 0. So series diverges by test for divergence. Okay. Okay, number 5. And I should say my number 5. Negative 1 to the n minus 1 over 2n plus 1. Okay, is it alternating? Yes, you can tell by this. Okay, that n minus 1 changes whether you start with a positive or negative. If you index beginning at 1, that'll make the first term positive. Quite often you want the first term positive. Are the terms decreasing in absolute value? Yes, which means if you ignore the negative 1, you have 1 over 3, 1 over 5, 1 over 7, 1 over 9, right? I mean, almost like the quiz. What am I doing? I'm plugging in 1, 2, 3, 4, right? 1/11th, 1/13th. So those are decreasing in absolute value, and they approach 0. Right? If I plug in a million, 1 over 2 million and 1, 1 over 2 billion and 1, that does approach 0. So how would I write it on the quiz or test or homework? It's alternating. Absolute value of a sub n decreases, and a sub n approaches 0. Therefore, therefore, the series converges by the alternating series test. Okay, and let's see, number 7. And number 7 does match, I think. Yeah, does match. Okay, summation negative 1 to the n, 3n minus 1 over 2n plus 1. Okay. But if you notice this, when n gets real big, ignore the negative 1 and positive 1, 3n over 2n, 3 halves. That means in the long run, it looks like plus 3 halves, minus 3 halves, plus 3 halves, minus 3 halves, etc. That will diverge. In other words, absolute value of a sub n approaches 3 halves. So a sub n does not approach 0. Therefore, the series diverges by the test for divergence, TFD. Okay. Right. All right, and the next few problems, I can tell that mine deviate from yours so much, I think I'd rather just go ahead and do some of these, right? So work them out as we go along, so to speak. So let me make this disappear, and I'll just work some problems out that I wanted to. I'm going to show you 11. So I'm working it out in real time. Summation negative 1 to the n plus 1, n squared n cubed plus 4. Okay, is it alternating? Yes, this tells me. Beginning with a positive or with a negative. Well, we put a 1, -1 squared, so it begins with a positive. Now, n squared over n cubed plus 4, for super big N, what do you ignore? 4. So it's like 1 over n. And I know those terms decrease, right? I mean, or another way you can say is this is second degree, this is third degree. So in the long run, this wins, right? So this is alternating. Absolute value of a sub n is decreasing. And do these terms approach 0? Yes. N squared loses to n cubed in the long run, always. A sub n approaches 0. Therefore, the series converges by alternating series test. So for these problems, quite often there's only two choices. Either it converges by the alternating series test or it diverges by test for divergence for the problems in this section. Okay. Now, here's a real tricky one. 15. Summation n equals 0 to infinity. Oh. Sine of n plus 1/2 pi over 1 plus radical n. It's kind of tricky. Let's see what happens when I plug stuff in. Let me do the denominator. If I plug in 0, I have 1. If I plug in 1, I have 2. If I plug in 3, I have 1 plus radical 3, and so on. Okay, plug in 0. Sine of pi over 2, 1. Plug in 1, 1.5 pi, that's 3 pi over 2. Sine of 3 pi over 2 is -1. Plug in 2, 2.5, 5 pi over 2, that's the same as sine of pi over 2, is back to 1. So here's a sneaky way of getting it alternating, in other words. Plug in 4, 4.5 pi, 9 pi over 2, -1 over 1 plus radical 4. Okay, so there are ways to get alternating besides the -1 business. Okay, this is a sneaky way of doing it. So yes, it is alternating. Okay, so it's alternating. Are these terms decreasing in absolute value? Basically, just ignore this. You can tell, right? This decreases in absolute value. Yes, it approaches 0 when n goes to infinity. This thing goes to infinity, so the ratio becomes 0. So absolute value of a sub n is decreasing, and a sub n approaches 0. So yes, therefore the series converges by the alternating series test. So that was a little bit tricky. All right, then let's see. 19, what time is it? 8:40, oh yeah, plenty of time. Okay, 19 is really kind of weird. N to the n over n factorial, -1 to the n equals 1 to infinity. So let's see. That one I actually have here. N to the n over n factorial. Is it alternating? Sure. N to the n over n factorial. This time starts with a negative. So it goes negative. How do I know it starts with a negative? If you plug in 1, negative 1 to the 1. It's negative 1. So positive, negative, positive. Okay, plug in 1, 1 to the 1 over 1 factorial. 2 squared over 2 factorial. 3 cubed over 3 factorial. 4 to the 4th. 4 times 4 times 4 times 4, 4, 3, 2, 1. 5 to the 5th. 5, 5, 5, 5, 5, 5, 4, 3, 2, 1. Can you see what's happening as I go from term to term? Let's go from here to here. Okay. Which is bigger, the top or the bottom? 4, 4, 4, 4, 4, 3, 2, 1. These are the same. This is bigger. So the top is bigger, right? The top wins. 5, 5, 5, 5, 5 is definitely bigger than 5, 4, 3, 2, 1. Next one, we'll have 6 sixes over 6, 5, 4, 3, 2, 1. So we're definitely not approaching 0. Right? A sub n does not approach 0. Therefore, the series diverges by the test for divergence. Okay. So that's that one. Okay, so this is the alternating series test. Fairly straightforward test. Okay, so I think I've done enough of those problems. There's one extra theorem to give you, and yeah, I think I can knock it off, and then that's pretty much about it. So for these problems, of which I've already done, what, a half or a third of them, okay, most of the answers are either going to be it converges by the alternating series test, or it diverges by the test for divergence. Okay, now what about the problems at the end? We have something called the alternating series estimation theorem. Alternating series estimation theorem. (735). Alternating series estimation theorem. Abbreviation, ASET, A-S-E-T. Alternating series estimation theorem. Again, this is all true, but say, what does it mean? If the sum of the series is summation negative 1 n minus 1 b sub n, b greater than 0, it's the sum of an alternating series that satisfies, basically it satisfies the alternating series test, then absolute value of r sub n is equal to absolute value of s minus s sub n less than or equal to b sub n plus 1. What does that mean? The error is no more than the next term. So let me show you my version of it. Alternating series estimation theorem. Put it on the next cheat sheet if you wish. Given a series that satisfies the alternating series test, if we stop adding after n terms, you don't feel like adding up infinitely many terms. I mean, physically you can't. You stop after n terms, the error is no more than the n plus first term, or the next term. Okay. So suppose I want to estimate the sum of the alternating series test. I already know it's ln2, but suppose we don't know that. I'm guessing you don't know that right now. 1 minus a half plus a third minus a fourth. Okay. Suppose I decide to stop right here. I don't feel like adding up infinitely many terms, right? You can't really do that. Okay, I figured this out. The error is no more than the next term, 1/10. Okay, so if I add up just these, I will be within 0.1 of the natural log of 2, or 0.693. Okay, that's what it means. Okay, and do I have time? Yeah, I think I have time. Let me actually try to add this up. You can try to do it too. So I'm going 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6. You can tell it takes a while to do this. Plus 1/7 minus 1/8 plus 1/9. Let me see if I did it right. .745 and 0.693. So yes, it is within 0.1. So by adding this up, I know I'm going to get something between 0.593 and 0.793. Yeah, you might say that's not very accurate. Well, how do you make it more accurate? Go farther. So you can tell you can get any desired accuracy that you want. You want the accuracy to be 0.00001, 1 in a million, just go out a million terms. Of course, you don't want to do that, but that's easy for a computer. Right? It's very easy to program a computer to add this up. Okay, and say my estimate for natural log of 2 is I can just go out to a million terms for this, and you get 0.693 whatever. Okay. So the error is no more than the next term. And again, the logic behind that is pretty straightforward again. If you think back to here, right? This back and forth stuff. Okay, so the series converges to S. If I stop anywhere, so let's say I stop adding B1, 2, 3, 4, and 5 up to here. The error is no more than the next term. So you can see by doing this, you always shoot past the true sum. Right? Notice in this progression, every time I go backwards, I'm always shooting past the sum. Right? So I go like that, I pass the sum. I go like that, I pass the sum. S. Go back, back. So if I say, okay, I don't feel like adding anymore, I'll stop at B5. The true error is the difference between there and S. How far am I going for the next term? I'm shooting past it. Right? So by virtue of the fact that you just kind of keep going back and forth, the error is no more than the absolute value of the next term. You see, so that's the logic behind it. So by going far enough out, you can get any desired accuracy that you wish. And since these terms approach 0, right? These approach 0. You can get as accurate to 1 in 1,000, 1 in a million, 1 in a billion, 1 in a trillion. Just go out far enough, punch it in the computer, and you get 0.6931 or whatever. Okay, so I'll show you a couple of those problems, and that's about it. And then I'll stop. Okay, so I'll be done in maybe less than 10 minutes, at which point you can ask me any questions, and if you don't have any questions, we'll call it a night. Okay, oh, and Thursday's quiz, I'll give you some series, and you figure out does it converge or diverge, but state why. Okay, so covering everything that we've done up to now. So here's a series. This series converges because, or the series diverges because. So just do the kind of stuff that we've been doing in class, sort of. Okay. My 21, which does match your 21. Very good. Okay, estimate the sum to 4 decimal places. Okay. Negative 0.8 to the n over n factorial. Okay. So let's see. How far do we have to go here? Up to 29. And yeah, that's just up to here. So I'll show you one of these. I'll show you one of these, and I think that's about it. All right. Whoops, this one. Negative 0.8 to the n over n factorial. Okay, so I wrote some of the terms out. They want accuracy to 4 decimal places, 0.0001. So I write some of the terms out. So when I plug in 1, negative 0.8 to the 1, here are the numerators. 0.8 squared, negative 0.8 cubed, positive 0.8 to the 4th. Okay. Denominators are 1 factorial, 2 factorial, 3 factorial, 4 factorial, right? Okay, is it alternating? Yep. Terms decrease in absolute value? Yep. And does it approach 0? Yep. Okay. I mean, just by this alone, right? Negative 0.8 to the n, that makes it smaller. And if I divide by something that gets bigger and bigger, that definitely makes it go to 0. Okay, so now estimate the sum to within 0.0001. So I have to go out until I get a term that's smaller than 10 to the minus 4. Okay, so you can punch this on your calculator. Okay, this 0.8 to the 6th power divided by 6 factorial, which is 720. Okay, this is 3.6 times 10 to the negative 4. 0.8 to the 7 over 7 factorial is 4.2 times 10 to the negative 5. Okay, so this is good enough. Okay, this is 4.2 times 10 to the negative 6 approximately. Okay, 4.2 times 10 to the negative 5, that's 0.00042. That's less than this thing. Okay, so all I have to do is just add these things up. So instead of adding infinitely many terms, I only add 6 terms, negative 0.5506. Now you say, that's not fair. I only added 6 terms up. You're supposed to add infinitely many terms up. You're going to have an error. Correct. But the alternating series estimation theorem says the error is no more than 0.0001. So I'm no worse than 1 part in what, 10,000? My error is no more than 1 in 10,000. So I know the true value is between negative 0.5507 and negative 0.5505. And if you need greater accuracy, just go out farther. Okay. So that's the alternating series estimation theorem. The error is no more than the next term. Okay, and then I'll do 23, and maybe that's all I'll do. Then I'll stop. Okay, so how many terms do we need to go to get the indicated accuracy? So negative 1 to the n plus 1 over n to the 6, with the absolute value of the error being less than 0.00005. Okay. So here's how you do it. So I just write out some terms. It begins with a positive. How do I know? Plug in 1, negative 1 squared, 1. So 1 minus plus minus. Okay, 2 to the 6, 1 over 1 to the 6 is 1. 2 to the 6, 3 to the 6, 4 to the 6. Okay, so I keep going until I get something smaller than 0.00005 or 5 times 10 to the negative fifth. Okay, this is 2.2 times 10 to the negative fifth. This is 6.4 times 10 to the negative fifth. So this is already smaller, right? 2.2 times 10 to the negative fifth is smaller than this. So I just have to add up this many terms, which is 1, 2, 3, 4, 5. Okay, so I just need 5 terms. Yes, it's alternating. Absolute value of a sub n is decreasing. A sub n approaches 0. Therefore, the series converges by the alternating series test. This particular question only asks you to say, how many terms do you need? So it didn't ask you to actually add them up. So I didn't add them up. Decided not to. Okay, and let's see. We do have to go out to 29. Okay, I guess I should do one of 27 and 29 for you. Okay, approximate the sum of the series to 4 decimal places. Okay, so I'll be doing this in real time. How about I do 27 for you? Negative 1 to the n over 2n factorial. Okay. So n equals 1 to infinity. Negative 1 to the n divided by 2n factorial. Okay, does it start positive or negative? Negative. So negative 1 over 2 factorial plus 1 over, plug in 2, 4 factorial minus 1 over 6 factorial plus 1 over 8 factorial. Is that right? Okay, so negative 1/2 plus 1 over 24 minus 1 over 720. I happen to have those memorized. I don't have these memorized. So 8 factorial is 40,320. Okay, this is 2.5 times 10 to the negative 5. And that's already, that's 0.00025. That's less than 0.0001. So that's good enough, right? They want it 4 decimal places. Okay. Does it fit the alternating series test? Yes, it's alternating. So it's alternating terms decrease in absolute value, a sub n is decreasing. If you ignore the signs, decreasing, and does it approach 0? Yes. I mean, look at how small this already is. A sub n approaches 0. Therefore, the series converges by alternating series test. Okay, now they want accuracy to 4 decimal places. So by the alternating series estimation theorem, okay, if you stop anywhere, the error is no more than the next term. Okay, so I'm stopping after just 3 terms. So again, the logic is, hey, you're supposed to add up infinitely many terms. You're only adding up 3 terms. There's going to be an error. Correct. The error is no more than the next term, which is 2.5 times 10 to the negative 5, 0.000025. That's already smaller than 0.0001. So I'm just going to add up these. And they want it to 4 decimal points. So negative a half plus 1 over 24 minus 1 divided by 720. Negative 0.4597. Okay, with an error of no more than 0.0001. So the true value is between negative 0.4598 and negative 0.4596 by only adding 3 terms instead of infinitely many terms. Okay. So there we go. All right, folks, and yeah, I can mark this off. 11.5. I'm done with 11.4 and 11.5. Okay, so that's it. So next time I'll do 11.6 and maybe some of 11.7. Actually, 11.7 is just a review section. We should be able to knock that off. But we'll see how it goes. It's just a review of all the different techniques that we've had. Okay. All right. So I'm going to stop the share and check the chat. Okay. So that's nothing else there. Okay. Does anybody have any questions? Because if not, we're done. But you may ask questions if you wish. Okay. So a reminder, while you think of any questions, next time I'll do 1 or 2 sections and I'll give you time for a quiz. The quiz will be, I'll give you some series and you will say this converges or this diverges because blah, blah, blah. Okay. So you have to tell me why it converges or why it diverges. Okay. So on the schedule, I'm up to 11.5. So next time, 11.6, hoping for 11.7, but we'll see how it goes. Okay. Anybody have any questions about something they want to go over now, please? Okay. When will the test be? It kind of depends on when we finish. So on schedule, it was, what was it? Thursday the 10th of December, I think. Yeah, on this schedule thing, I'm aiming for Thursday the 10th, but I'll let you know when it gets closer. At least that's what I'm hoping for. Okay, anybody else, please? We don't have class on Thanksgiving Day, so this Thursday we meet. We don't meet on Thanksgiving Day, which is November the 26th. Okay, so come to class Thursday. We have class Thursday. That's too early for Thanksgiving. It's the Friday after that. All right, let's call it a night then, folks. All right, so everybody have a good night, and we'll see you next time. Okay, thank you, everybody. Bye. Have a good evening.
Bye, Mr. Holm. Have a good week.